Hi everyone, my name is Kristina Monsch and I'm a PhD student based at the LMU in Munich, and I'm working together with Barbara Ercolano, Thomas Preibisch, Giovanni Picogna and recently also with Willi Klei. And my work has been focusing on studying how X-ray driven photoevaporation can affect the orbital distribution of giant planets. And with the recent wealth of exoplanet detection, several trends have emerged from the data. And of course, understanding what controls the architecture of exoplanet systems is crucial to assessing their habitability. So if you plot the orbital distribution of all detected giant planets versus their mass, you see that they are not distributed homogeneously, but they pile up in specific regions. So here, for example, you have the hot Jupiters orbiting the host star very close, then you have the warm Jupiters at intermediate distances, and then the cold Jupiters at distances from hundreds to thousands of AU. And there has been quite some work done in this field to try to explain and reproduce these observed features in the distribution of giant planets. And during this talk, however, I'm only going to focus on the evolution of warm Jupiters and what sets their final parking location. So it has been suggested a few years ago that this dispersal via EUV and especially X-ray photoevaporation can reproduce the observed pileup of giant planets at around 1 AU. So the first question I want to answer in my talk is how does X-ray photoevaporation impact giant planet migration? And this is a very simple concept. So the energetic radiation which is emitted by the host star heats the gas in the surrounding disk so that it becomes unbound near the so-called gravitational radius. And from this radius on, the gas is then removed by pressure-driven disk winds, and therefore a gap is opened, so that the inner disk is cut off from further mass supply by the outer disk. And planets inward to this gap continue to migrate, while the inner disk is accreted by the host star. And as type 2 migration is only possible as long as there's gas available in the disk, the planets can either fall into the host star if the disk is not dispersed in time, or they are parked close to the star if the disk is dispersed quick enough. And while the inner disk is viscously drained, the outer disk is directly irradiated by the host star and removed quickly on a timescale of a few 100,000 years. So therefore planets in the outer disk also migrate inwards. However, they are at the latest stop once they reach the photoevaporative gap. And this means that the location of this gap, which is opened by photoevaporation, can define the final parking location of the planet. However, the location of the gravitational radius, as well as the timescales in which photoevaporation is able to remove the disk, very much depend on the photoevaporation profile you assume. So here in the top right, I'm showing you a plot of the normalized mass loss rates of 3 different photoevaporation profiles as a function of the distance to the central star. And you see that the EUV profile is mostly efficient in the inner disk and peaks close to the gravitational radius, while the X-rays can penetrate the disk deeper and therefore remove the disk more efficiently on a larger scale. FEV photoevaporation is mostly efficient in the outer parts of the disk and therefore especially considered to be important in dense stellar clusters, for example. And what is important to note here is that this plot here only shows the normalized mass loss rates. So if you plot the total ones, you will see that they differ by up to 2 orders of magnitude, meaning that they will shape the disk in very different ways. And therefore, we also expect that they should leave an imprint or a different imprint in the observed distribution of giant planets. And the effect of these different photoevaporation profiles on a given population of giant planets had been studied by Jeff Jennings, Barbara Ercolano, and Giovanni Rossotti a few years ago. And indeed, they found that applying these different photoevaporation profiles will lead to very different orbital configurations of the planets. So can we actually observe any signatures of X-ray driven photoevaporation in the orbital distribution of giant planets? And for this purpose, I have constructed a catalog during the beginning of my PhD, and this catalog contains the X-ray luminosities of all giant planet host stars that had been detected back then to investigate if X-ray photoevaporation leaves any characteristic features in the observed distribution of giant planets. And since we were looking for a correlation between the stellar X-ray properties and the orbital distribution of giant planets, we plotted the stellar X-ray luminosities versus the planetary semi-major axis. And there we found an interesting feature, which is this tiny gap here, centered on around 10 to the 28 ergs per second, and which is located between 0.1 and 1 AU. And here we think that this is due to photoevaporation, creating a parking radius for the inward migrating planets. However, unfortunately, due to the small sample size, we could not show the statistical significance of this void without having an accurate theoretical model that would predict the exact location and size of this gap. For this purpose, we have therefore performed a simple planet population synthesis using the 1D viscous evolution code SPOC. And we used a very simple setup of a 0.7 solar mass star, where the disks have 10% of the stellar mass, and then giant planets of random mass between 0.5 and 5 Jupiter masses are inserted into the disk and then migrate as the disk is being dispersed by viscous accretion and X-ray photoevaporation. I want to note here, however, that this code does not model the planet formation itself, but only the evolution of the planets. Yeah, and already in this very simplified model, we were able to produce a similar feature as the one we have seen in the observations. And here we actually know that this gap is due to photoevaporation carving a gap into the disk and therefore parking the inward migrating planets. However, while these results are very promising and exciting, we need to be quite careful because first, 1D models always suffer from the major simplifications you have to assume to be able to run a statistically significant amount of simulations. And second, this plot here is the result of very specific initial conditions. So by changing the initial setup just a little, we were actually able to change the final outcome drastically. This was, for example, that we were able to refill this gap entirely or remove many features that we have seen before, like this pileup of planets outside of the gap. And this is, of course, problematic because we theoretically predict this gap to exist. So therefore, we had a closer look at the surface density evolution of the planets that ended up in this gap. And there we found another very interesting thing. So the planets in our population synthesis migrate following the impulse approximation, which is basically described by this equation that you can see here. And for some cases, we found a strong inward migration of the planets that were pushed inwards by a very massive outer disk, while no inner disk was present anymore. And such systems can be explained by the so-called pipe effect, which means planet induced photoevaporation. So giant planets that are massive enough to open a gap will reduce the inflow of mass from the outer to the inner disk, and therefore photoevaporation can kick in earlier as would be theoretically expected. Photoevaporation can therefore remove the disk inside of the planet on a very short time scale so that only a massive outer disk remains, and such disks would correspond to transition disks with an evacuated inner cavity. And in our 1D model, this outer disk is then pushing the planet inside at an increased migration speed, because there are no inner disk torques left to counteract this effect. However, these 2D studies I've just mentioned did not investigate in detail the migration process of the planets, and it's therefore not clear if this effect that we observe in 1D is actually realistic. So do giant planets actually migrate in transition disks with evacuated inner cavities? And the only way to answer this question is by modeling such systems in 2D. For this purpose, we modeled the combined effect of X-ray photoevaporation and giant planet migration in the 2D version of FARGO, both in primordial and transition disks, which have an evacuated inner cavity. And this plot here shows the first important result from this analysis. So here we compare the migration tracks of the planets modeled in 1D using the impulse approximation, which is shown here on the left, and in 2D using FARGO, which is shown here on the right. And this is then done for different initial disk masses, both in primordial and transition disks. And what you can infer from this plot is that FARGO clearly shows us that planets embedded in transition disks with evacuated inner cavities will only migrate weakly. And this is basically the opposite behavior that is observed in 1D, where we use the impulse approximation, because there you see that the planets that are embedded in transition disks have significantly higher migration rates than the planets which are embedded in primordial disks. And the reason for this discrepancy between those two approaches is quite interesting. So here's a comparison of the radial distribution of the torques from both approaches, and what we found is that in the case of primordial disks, the impulse approximation is strongly overestimating the contribution of the torques from the co-rotation region close to the planet, while it underestimates the Lindblad torques, which come from larger radii and from which we actually know that they are the driver of planet migration. And in the case of transition disks, which is shown in the lower row, strongly positive torques will develop at the gap edge in FARGO, and these will effectively act as a planet trap, preventing any further inward migration of the planet. While in the impulse approximation, you see that they are positive and negative torques that will continue pushing the planet inside. So the conclusion from our analysis is therefore that this strong inward migration due to these one-sided torques that we have observed in our 1D code is unrealistic and should not be happening. And this means that planet migration should stop once the disk inside the planetary orbit gets depleted. Therefore, the impulse approximation is not treating planet migration, which is subject to one-sided torques, correctly, and this definitely needs to be taken into account in 1D planet population synthesis approaches. And I'm running out of time, so I will leave you with my conclusions, and thanks a lot for listening, and let me know if you have any further questions or comments. Thanks.